Welcome back, Physics 30. This is the second video in the CO1.7 section. So in this one, we're going to look at car horsepower. So it says power needs of a car. Calculate the power required of a 1,400 kilogram car under the following circumstances. So we'll look at the car as it's climbing a 10-degree hill, fairly steep hill, at a now constant speed, a steady speed. That's a key thing. Constant speed means F net is 0. Okay, and how I have this drawn, you may recognize this as yes, FG pulling downwards, and so if I just kind of redraw it, I'll exaggerate it like that. Yes, we have F perpendicular, which of course is equal to Fn. Then we have F parallel, which is equal to, call it applied down the plane. Okay, so we're going to have resistance forces, also the force going down the plane due to the angle of that plane. And then part B, the car accelerates along a level road and goes from 90 kilometers per hour to 110 kilometers per hour in 6 seconds. Assume the average, so the force is working against you in this scenario, 700 newtons. So there's quite a few different things we're going to have to figure out here. So we're looking at power. Okay, so for power, we need to know the work done. To know the work done, we need to know the overall force being involved. So let's look at this. Fg is equal to mg. We're going to have to figure out that first of all. It's a 1,400 kilogram car. Negative 9.8, negative 13,720 newtons is working against you. So now we know Fg, we should be able to figure out all of this. This, of course, is a 10-degree incline, which makes that triangle there 10 degrees. So we can find F parallel, and we can find F perpendicular. So F parallel, of course, is the opposite side. So that's sine equals F parallel over Fg. Now don't worry about using the negative, just use the magnitude. So 13,720 multiplied by sine of 10. So that's going to give us for F parallel 2,382.45 newtons. Let's leave it like that for now. Let's see, what else do we need here? Now we're not told anything about friction here, so we likely won't have to worry about F. We're just simply told that all of our retarding forces that are working against you are simply that. So let's look at up the hill. That is very similar to like horizontal. So whenever we looked at that, it's kind of like horizontally what's going on. So F net, we have a couple of things going on here. We have FA, the applied force. Now, I should be I'm just going to get rid of that, just simply call that F. By applied force, I'm talking about what force must the car apply to go up the hill. So we have that force. We also have F parallel, which is due to the incline, the force that's pulling us downwards. And we also have FR, kind of the friction, the forces that are working against us. So that has been simplified just to simply say, okay, all the forces, tires, etc., working against us is that. Now, since we're told steady speed, we know, of course, this is equal to 0. And so if we assume that we're applying the force to go in this direction, that's positive, then that means these are going to be negative. Negative 2382.45 working against us, as well as this 700 is working against us as well. Okay, so just like before, we have to look at our directions and see what's working with us and what's working against us. So if I combine these two, I get 3082.45. Add that to each side. And FA works out to be 3082.45 is what I'm going to have to apply to go against that. Okay, 3082.45. Of course, we could round that off to 2 sig figs, 3100. But if I'm using it as a in the calculation, I'm going to use the non-rounded off answer. Okay, so a couple of things here. Let's see here. Now we're moving at a steady speed of 80 kilometers per hour. And of course, if you recall to change that into meters per second divided by 3.6. And using my new power formula, the applied force I have and the constant velocity I have, so I can figure out everything that I need. So power is equal to the force I'm applying. Again, use the non-rounded off version. 22.2 meters per second. So that's going to give me 68,430.39 watts. But I'll round that off to 2 sig figs. 68,000 watts. Okay, so looking at, so there's two ways we could figure out the power, of course, work over time. We weren't told anything about time here, so that's going to hopefully involve the other power formula that we have, in which we can figure out the applied force that we're exerting, how fast we're going. We can figure out power in that fashion. Part B. So we were initially going 90, then we go to 110. So of course we have to figure out what each of those is in meters per second. So divide by 3.6. My final velocity, 110 kilometers per hour. So that's 30.6. Okay, so we have a V initial, a V final, and what else do we have here? That all happens in 6 seconds. So if we have that, that helps us figure out what acceleration is going to be. So to reach a velocity of 30.6, initially going at 25, to make that happen in 6 seconds, the acceleration must be 0.93 meters per second squared. Okay, with that, if I know acceleration, I can get net force as usual. So my 1400 kg car, to accelerate at 0.93 repeating, it's going to involve 1,306.622 newtons. So that's my net force. Now, in this one, we're not going up a hill, it's just simply horizontally. So F net is my applied forces, and then all my forces working against me. So this time, horizontally, I don't have this component of a force that's working against me due to being inclined. It's just simply a flat surface. So F net, it looks like I am accelerating, so I have to plug in that number there. And of course, force is working against me, 700. So add 700, add 700. FA is equal to 2,006.622. Then I can, then again, so I have my applied force. Power is equal to force multiplied by V. So the force that I need to apply to get a net force of 1,300, of course, I have to apply a lot more because some of it is getting used up due to overcoming the friction forces. Now, for here, I'm going to just simply use max velocity. So in order to achieve the maximum velocity of 30.6. Okay, you can use that. Otherwise, I would state in the question exactly what I would need you to do. And I'm running out of room here, so I'm just going to give you the rounded off answer, 61,000 watts. All right, so that question kind of brings in a lot. Like a lot of the things that we talked about brings in some of the previous unit in which we analyzed triangles like that. We also looked at the work equation, power equation, etc. All right, looking at the last page here, only part of the energy output of a car engine reaches the wheels. Not only is some energy wasted in getting from the engine to the wheels, in the engine itself, most of the input energy from burning gasoline or other fuel does not do useful work. An important characteristic of all engines is their efficiency. How efficient are they? And it's a ratio of output to input in terms of power. So what we get out of it versus what we get into it, of course, the closer we achieve an answer of 1, the better that is. So the efficiency is always less than 1 because you'll never get out of it completely what you put into it. No engine can transform energy from one form to another without some energy going to friction, thermal energy, and other non-useful forms of energy. For example, an automobile engine converts chemical energy released in the burning of gasoline into mechanical energy that moves the pistons and eventually the wheels. But 85% is wasted, which is a huge amount. It's going out the exhaust pipe as thermal energy, friction, etc. Cars overall are only 15% efficient. So you can see not very efficient there at all. Now when you're doing the assignment here, ladies and gentlemen, CO1.7, you'll be able to see on the answer key, etc., how to do a lot of the things. Of course, we use the power formula here. Some of the questions, though, you're going to have to, they're similar. I think I have one that's similar to that card, in which there's a couple of things you're going to have to figure out. But realize that, of course, that power equals work over time. And, of course, work. In order to calculate work, you may have to calculate change in energy in some way. Okay? And, of course, that energy could be a change in kinetic energy or a change in potential energy. So sometimes you have to figure out change in potential or change in kinetic. All right? So you should be able to do the assignment for that. If you run into a snag, just look at the answer key and hopefully you can get a hint that you need. All right, we'll see you again.